All right, let's take a look at this PowerPoint for chapter 2.3. We're still in the chapter of set. In section 2.3, we'll be looking at set operations. Our goals are to perform the set operations of union, intersection, complement, and difference, to understand the order in which to perform set operations, know how to apply De Morgan's law in set theory, use Venn diagrams to prove or disprove set theory statements, calculate the cardinal number of the union of two sets. Union of sets. Definition. The union of sets A and B, written A union B, is the set of elements that are members of either A or B or both. Using set builder notation, then A, a symbol that looks like U, standing for union, A union B equals the set of all X such that X is a member of A or X is a member of B. The union of more than two sets is the set of all elements belonging to at least one of the sets. For example, find the union of the two sets 1, 3, 5, 6, 8 for A, and B is the set 2, 3, 6, 7, 8. Then the set of elements that are in A or B or both are the elements 1, 2, 3, 5, 6, 7, and 8. Intersection of sets. Definition. The intersection of the set A and B, written A intersect B, is the set of elements common to both A and B. Using set builder notation, we have A intersect symbol, which looks like the union, but only opening downward. A intersect B is the set of all X such that X is a member of A and X is a member of B. The intersection of more than two sets is the set of elements that belongs to each of the sets. If A intersect B is the empty set, then we say that A and B are disjoint. Example, find the intersection of the two sets. If A is 1, 3, 5, 6, and 8, and B is 2, 3, 6, 7, and 8, then A intersect B, which it looks like it typed up funny, A intersect B is the set 3, 6, and 8. Now, if we go back a slide, we can look at the Venn diagram. In this Venn diagram, we have a universal set, that's our orange proof. We have the set A, that's our green region, and we have the set B, that's our blue region here. Now, the set of elements belonging to A are shaded here. And the elements that belong to B are shaded here. Now we have shaded all elements in A or B or both. And in the next slide, clear that off. In the next slide, we have the elements that are in A and also in B. So if you're in A and at the same time in B, then you're in this center overlapping region of the Venn diagram. The set complement definition. If A is a subset of the universal set U, the complement of A is the set of elements of U that are not elements of A. This set is denoted by A apostrophe. Using set builder notation, we have that the complement of A is the set of x's, all x's, such that x is an element of U, but x is not an element of A. For example, if U were the numbers 1, 2, 3, that's supposed to be a dot, dot, dot to 10, then A is, oh, I thought maybe I could change it. This here, though, I could at least draw over it. That's supposed to be dot, dot, dot. 1, 2, 3, dot, 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 10. That means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And A is the elements 1, 3, 5, 7, 9. So the elements that are in U, they're not in A, are 2, 4, 6, 8, and 10. In our Venn diagram, we've shaded everything on the outside of A. Everything on the outside of A is shaded. That's the picture of A complement. Set difference definition. The difference of sets B and A is the set of elements that are in B but not in A. The set is denoted by B minus A, or B take away A. Using set builder notation, we have that B without A is the set of all x's such that x is a member of B and x is not a member of A. For example, find the difference of the sets 3, 6, 9, 12. Take away the set such that x is an odd integer. So if we take out the 3 and we take out the 9 from the original set, because those are odd integers, then we are left with the set 6, 12. And visually, B without A is to look at the B region and shade everything except for regions of B that are also in A. Order of set operations. Example, let the universal set be 1, 2, 3, dot, 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 10, and let the set E be all x's such that x is even. Let the set B be the set of 1, 3, 4, 5, 8, and let A be the set 1, 2, 4, 7, 8. Find A union B complement, intersect with the complement of E union A set. And we have to follow steps in order to achieve this. So the first thing that we can do is union set A and B. And then we can take the complement. Then we can take the complement of E so that we can union it with A. And finally, finally, then we can intersect the two sets. So left-hand side, right, versus the right-hand side. Left-hand side, we can first union A with B. So A is 1, 2, 4, 7, and we union that with 1, 3, 4, 5, 8. Union is everything everything, right? So everything from both sets. So we have the 1, we have the 1, writing 1, 2, 4, 7, 8 from A, and we have the 1, 3, 4, 5, and 8 from B. So every element from A and every element from B. And now we look at the complement of that set from number 1, from step 1. The complement is every element in U that's not in A union B set. So we're crossing out the 1, the 2, the 3, the 4, the 5. We're still left with the 6. Cross the 7, the 8. We're left with the 9 and the 10. So all the elements in U after we remove A union B are 6, 9, and 10. Now that's the end of the left-hand side. That's the left-hand side ending right there. Excuse me. Now on the right-hand side, inside of the parentheses, we have the E complement. The E is X such that X is even. So everything in U that's not even, because E complement is to take U and remove all elements from E. So all of the odd elements are left because E was even, leaving us with the set 1, 3, 5, 7, 9. And now we're going to union that 1, 3, 5, 7, 9 with the A set, which is 1, 2, 4, 7, and 9, 8. So E complement union A is 1, 2, 3, 4, 5, 7, 8, 9. And that's the right-hand side. So line 2 represents the left-hand side. That's our 6, 9, and 10. Line 4 represents the right-hand side. That's our 1, 2, 3, 4, 5, 7, 8, and 9. And now we have the intersection of these two sets. The intersection is what they have in common. It's either a 6, 9, or 10, or all of the above, or some subset of that. There's no 6 in the blue set. There's a 9. There's no 10 in the blue set. So the only thing those two sets had in common was that element 9. Order of set operations continued. Here we're looking at the De Morgan's laws for set theory. We'll use these again in logic. If A and B are sets, then if we union A and B and then take the complement, that's the same as taking the complement of each set and intersecting. And also, if we take the intersection of two sets and then complement it, that's the same thing as complementing each set and then taking the union. So A union B complement equals A complement intersect B complement, and A intersect B complement equals A complement intersect B complement. And it looks like we need to clean up some of this typing. I's, of course, stand for intersecting. So I'll replace those with intersections. Intersection distributes over union. So another equation that people use is if you have A intersect the quantity B union C, that's the same as A intersect B union A intersect C. So we get the same results. The cardinal number of the union of two sets, if A and B are sets, then the cardinal number of A union B is the number in A plus the number in B minus the number in A intersect B. Oh, let me draw this picture. Because if we look back at one of our original drawings, A, B, universal set. A was green, I believe. So if we're counting all the elements in A and counting all of the elements in B, then you can see that I have twice counted this section in the middle. That section in the middle is the overlap. That's what these two sets have in common. And that is called A intersect B. So the number of elements, if we look at B and, or if we look at the green and blue together, then we're looking at the shaded region A union B. So the number in A union B is the number in A, the green ones we counted, plus the number of elements in B, the blue elements that we counted, minus one copy of the number of elements in A intersect B, because we counted them once when we counted the green elements, and we counted them a second time when we counted the blue elements. So we have to remove it that second time.